Sure.
The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, ladies and gentlemen. Welcome to Bruker Nanosurfaces Metrology's webinar on an overview of surface roughness measurements, choice of techniques and analysis. My name is Sue Thing and I will be hosting today's webinar. Before we commence, we would like to share that all attendees would be on listen-only mode. There is an opportunity to interact with us and we encourage you to ask questions in the questions window. There will be a 15 minutes presentation followed by Q&A, which our speaker will answer at the end of his presentation. If we are unable to respond to all your questions due to time limitation, we will respond to you through email. I will now pass the floor to our moderator, Mr. Lau Wei-Chi, APAC Regional Manager for Optical and Stylus Profile Emitters for Bruker Nanosurfaces Metrology. Mr. Lau, please.
Good afternoon, everyone. My name is Wei-Chi. It's my privilege to introduce Dr. Ashar Abu Zubaida, for our speaker for today. Dr. Ashar is an application engineer at Bruker Nanosurfaces, responsible for application and technical support of nanomechanical and survey metrology instruments. His academic background was in material science and atomic force microscope. Dr. Ashar obtained his Ph.D. from Jawaharlal Nehru Center for Advanced Scientific Research, majoring in surface engineering of polymer thin film for charge transport applications. Prior to joining Bruker, Dr. Ashar was a research associate at the center. He has published multiple peer-reviewed international journal papers and has also presented at multiple national and international conferences. We now invite Dr. Ashar to share with us on this topic, an overview of surface roughness measurements, choice of techniques, and analysis. Dr. Ashar, please.
Yeah. Hello, everyone. Welcome to the webinar. Thanks for the introduction. Thanks for shooting and Wei-Chi. So, as many of you are, we are also working from home. Hope we can use the best out of this webinar. This webinar is basic introductions to surface measurement methods. We encourage you to ask questions during the webinar. So, what you can expect today. This is the list of things I have planned for you. So, what's the importance of a surface texture? And then techniques to measure surface structure, how to choose your instrument, and then Bruker's solutions to the surface structure measurements, in which we will be focusing on DECTAC and optical profilers. And then we will move on to 2D and aerial filtering and some practical examples for data analysis if the time permits. So, hello. Yeah, sorry for the disturbance over here. So the surface structure, as you see, it's a complex condition resulting from a combination of roughness, waviness, lay and flow. So if you take a workpiece, then you can see multiple profiles in that. Such as roughness, which is process and material dependent, typically of, depending upon the length scale, it is of lower wavelength. Then you will have waviness. This will be basically originating from vibration, chatter, or work. The waviness will have much longer wavelength compared to the roughness, or in other words, special frequency wise, the roughness will be the highest special frequency, and waviness will be lower special frequency compared to the roughness. And then roughness plus waviness form surface structure. People use the roughness and surface structure as synonymous. but the right definition would be to use surface texture as roughness plus waviness. And then you will have a shape or a form which is associated with the workpiece or the surface. So this general shape of the surface is due to inaccurate machine or stress parts. The form will typically have the longest wavelength. And when you start measuring a surface, you start with a raw measurement, which then will be filtered electronically to make a primary profile. So certain cutoffs are applied to take out the primary profile from the raw data. We will be discussing that as we go along. So these are the typical surface roughness numbers produced by processes in the manufacturing process. If you want this, the slides, you will be getting it later. So why we are interested in the surface structure? So the simple answer is that it affects day-to-day life, because you have a car and it has a brake. So you will be worried about when you break the system, it needs to stop at the right moment. So if you look at the two surface textures measured over here, so these two surfaces will have the same RA, the average roughness, but they perform differently. Similarly, now if you have a car and you typically like it, good finish, but if your paint is or the surface is not so good, then you will get something like an orange peel effect, which you don't want. And similarly, a fuel sensor, a nominal wear would look like this, but a failed component would look like this. So you need to look at the surfaces and its profile to understand what's the functionality, how it is going to perform. So in a manufacturing environment, one needs to have control on the process to deliver the desired specification and tolerance for the product. So similarly, functional surfaces need to be diagnosed and functionalities need to be predicted. So this requires constant inspection and quantification of the interacting surface. So typically one would like to go from manufacture to performance, but you need to have a measurement step involved. So starting with any surface, you keep doing the measurement to understand what's the surface properties. So surface now I will move on to the surface texture measurement techniques. So this will be an overview of what all can be used for measuring the surface texture. So one of the obvious answer would be an atomic force microscope. So this will be using a AFM typically uses a deflection of the laser beam bounced back from the back of the AFM probe, which will be then collected by a detector. So the tip will be of a diameter of few nanometers. So the deflection of the probe will monitor the surface. So the probe will be connected to a piezo whose movement is controlled precisely using fast electronics. So the pros are here highest zero solution, such as less than 0.01 nanometer, and simultaneous imaging of multiple properties. And you can do the imaging by contact or non-contact. So, but there are cons like you have limited XY range. So if your sample have probably millimeter range inspection, then this won't be a good idea. So, and you need to have special sample preparation and good expertise for operating the AFM. Now, another option would be Stylus surface profiler, where you will have a stylus which is connected to a transducer. So the movement of the stylus is monitored by the transducer, and which that signal is then fed to the computer for the analysis, which will apply a different kind of filters, and then we will understand the surface from the measure. So Now, the pros are here you have high Z resolution around 1 angstrom and long scan length, typically 55 mm in our case, in our detect, and excellent repeatability, and you can even do 3D measurements. But there are cons like it's a contact method, and 3D measurements are slow. And then confocal microscopy. This picture is a very oversimplified version of the confocal microscopy. Basically, confocal microscopy uses conjugate points, such as if there is a light which is reflected off from this point, which will be specially filtered using a pinhole over here, so that all the outer focal volume data from this point will be eliminated. So you will be exactly measuring the light which is reflected back from here, which goes back to a CCD, or in the case of an XY scanner with PMT, this light goes back to PMT. So here the pros are the vertical resolution of 3 nanometer and lateral resolution of a few hundred nanometer. But there are cons like the resolution is dependent on the objective which you use, and signal decreases and become unreliable for high surface slopes. Now we move on to the main one of the main areas for today, which is white light interferometry. So before going to that, let me give you a brief introduction to what's interferometry. So let's start with the light. Light is a form of energy. So you can represent it as a wave, and wave will have an associated 3 parameters, which is a wavelength, amplitude, and phase. So if a wavelength will be the length from starting from here to completely the cycle over here, and then the amplitude is the distance between the mean to the crest or to the depth, and then there is an associated phase which we will come as we move on. So the phase of the wave here, as you see, there are 2 waves overlap. You cannot see the 2 as they are actually overlap. They are called in phase. Now, if you move one of the wave a little off, then you can see these 2 waves, where these 2 waves are offset by theta. This theta is called the phase difference. And if you offset even more, then they are like completely out of phase, which is called 180-degree out of phase. So what can you do with these waves? You can do a constructive and destructive interface. That means you can add them or do a subtraction kind of. So let's take wave 1 and then put a wave 2. And if you orient them in such a way that the crest of one of them matches with the crest of the second one, you will typically get a constructive. You will get a constructive interference. Sorry that the second wave is a little bit moved. Ideally, this should have been overlapping the crest. But if you do the similar kind of an addition in case of wave 1 and wave 2 in this fashion, where the crest of them meet the trough of the second wave, you will get a destructive one. So what will be the result? You will get a typical interference pattern when you put 2 flat surfaces. So we are going to use that principle in the implementation of the 3D microscope. So an interferometer is an optical device. It divides the beam of light and then it combines back. So to schematically represent, let's look at the figure here. So you have a source of light which sends the light to the beam splitter. So the beam splitter split the light, one reflected, one transmitted, and then it goes to a sample and then it is reflected back. So the light is reflected back from the sample as well as the reference mirror. So as we discussed earlier, there will be an interference taking place over here, which will be collected at the CCD, which later develop the interference pattern for us. So this is the simple principle of how the white light interferometry works. Now, if you put two surfaces, two planes, in this slanted fashion, as you move along from this point to this point, since the distance is varying from the left end to the right end, you can find places where there are lengths of lambda, then there is another length of 2 lambda, then there is another length of 3 lambda. So in that cases, you can see, since the interference criteria satisfies over here, then you can actually see fringes developing due to the interference. Now, let's look a little more deeper how we are going to proceed with the this method, this principle in our device, in our instrument. So let's take a blue light which has a lambda wavelength of lambda b, and it has an amplitude pattern. Sorry, this should have been amplitude. So if you add more lights, like now it's a green light, let's add yellow, then let's add red. As you see in the progression, as we add more and more light, you see this amplitude pattern varies. So this is what happens when you take a white light and do an interference. And this is a representation of a white light because it consists of the light from blue to red. And this will result in an amplitude pattern, something similar to this. This is what we are going to use in the white light interferometry. So first, one of the methods which we use in the white light interferometry is the vertical scanning interferometry, where we scan the interferometric objective down in the z-axis, and then as animation shows, as the focus passes through certain points, it gives the interference patterns for each frame, which then is given to a computing algorithm to process back and give us the surface structure. So we have a noise floor of 3 nanometer, and you can actually do a 10 millimeter measurement in the system, and slopes of 60 degree plus can be measured. The limitations are that slopes of the sample surface, sometimes you need to be careful about the surface when you are selecting the objectives. So it will be challenging for transparent ultra-thin films. It's not that it's not doable. We can do it. Then if you have dissimilar material with refractive index, then you need to have some prior information. So still, it is we can tackle the problem. Now, in the next method which you use is the phase shifting interferometry, which is called PSI. The VSI, as we mentioned earlier, these are typically used for little rougher surfaces, but relatively our very smooth surfaces, we use the phase shifting interferometry, where we use the phase, the advantage of the parameter of the light, which is the phase. So what we do here is, if you look at the interference intensity, you have a term called I background and I amplitude, which is coming from the interference, and there is a cosine factor over here. So so you can actually measure the object phase from the phi, and if we can do a slight phase shift between different wavelengths, and since this is an equation, we can get back the measured object phase from multiple measurements. How we are going to tackle it? So we can take 4 different measurements where we just shift the phase in this equation, which is basically done by small movement of the piezo, which actuate equal length of lambda by 4, and then once it completes a full lambda, then you will get picture 1, picture 2, and picture 3, picture 4. For each of them, you can measure the I of xy, and then from this trigonometric relation, and then simple simple equation, you can get back the phase. From phase, you can calculate the height of the surface over here. So it basically gives you it's helped you to find the surface roughness in very ultra smooth surfaces. Now there is the third mode, which is VXI. So VXI uses it's a combination of VSI as well as PSI. So here it uses complete optical signal for optimum universal result. So the advantage over here is that it's self-sense smooth or rough surfaces. So here you can see a one VSI image taken of a surface, where the same image when performed with the VXI, we get much better features, because over here you see that these surfaces are underrepresented, but the true representation of the surface can be taken out by the VXI measurement. And how can we do? If you are familiar with the vision, you can use the measurement option over here, in which VSI and VXI are given in the same in the drop-down menu, and then you can select the method or the processing method as VXI. So this says that the VSI and the VXI measurement method is the same, but the algorithm is going to be different. So because of that, there will be a little bit of extra time taken during this measurement. Now we will move on to the next one, the focus variation. So here, basically, here the method of measurement is the same. We move the field objective down over here, and then instead of an interference pattern, we look at the best contrast. So if you take a picture of, put the focus of a camera over here, and then measure, take a photo, and then next put the focus over here, you get a second photo, and then you add, you will get the contrast from this picture. So you develop that over all the pixels, over all the length down over here, which will give you the focus variation. So so the confocal requires this is just a comparison slide for confocal versus focus variation. So confocal as well as white light requires the light to come back in the same way it was sent. So this says that if there is a large slope, we will be having light loss. But if you have focus variation, you can actually use external lighting to increase the contrast over the surface, so that you will get much better measurement from rough and large area samples. So also the focus variation have the advantage of high speed. So this will help us to collect a large amount of data. If you look at the number, the 60 seconds, with the kind of volume which we are looking at, this is actually not achievable by white light interferometry. It can be done by the focus variation. Now, which surface technologies to use? So this will give a sneak peek of what kind of decision you have to make when you're looking for a proper surface technology measurement. So here on the horizontal axis, you have a lateral resolution. On the vertical axis, you have height. So the highest performance or highest lateral resolution, and then is given with the AFM, but it has a height limitation of around 10 microns. So you cannot measure something like 100 micron. So then the next option can be, next and best option would be with the descent, and actually it's a good lateral resolution. You can use the white light interferometry as well as focus variation. Also, you can note that the Stylus actually covers the mid-range over here. So the advantage being the Stylus is that you can use this for any transparent media, which is transparent media thickness measurements, which is going to be a little tough with the white light interferometry. So then you can look at the vertical and the lateral resolution between the white light interferometry and the focus variation. So the white light interferometry represented in the blue represents the lateral resolution of around less than 1,000 micron, which is very smooth surfaces. But when you look at the focus variation, you will be typically looking for rough surfaces, but with the large field of view. And this will give a tabular construction of comparison between all these techniques. Now, Bruker solutions to surface measurements, we have AFM, then we have a 3D optical microscope and Stylus profilometer, and then for the tripod testings, we have tribometers. And additionally, we have Alicona, which uses the focus variation, which is not included in the slide. Today, we will be focusing only on the Stylus profilometry and 3D optical microscope. So now let's go to the roughness. So when we start talking about the roughness, the first thing to think about is the norms, because the norm determines everything about the roughness. So in the current scenario, we have three schools where one is ISO, then ASME, and JIS. So European auto industry typically follows ISO, and United States follows ASME. Also, the Western Europe countries such as Germany and France follows the ISO. For the access of the US market, the Eastern Europe countries typically prefer ASME. And as mentioned earlier, the Japan follows GAS. So the comparison between these these three norms between the 2D and 3D roughness is shown here. So in the ISO, you have a counterpart in over here with ISO 25178. But if you look at the 2D reference parameters in the ASME, there is no real equivalent over here. Also in the JIS, there are no such equivalent between the 2D roughness and 3D roughness. So there are people who uses the 2D roughness in ASME and JIS interchangeably with the 3D roughness, and that's okay. So now let's move on to 2D filtering. So selecting cutoff. So when you're talking about filtering, you will be thinking about what cutoff you use, what's the kind of the length scale which you are looking for. So this can be represented in this figure. So this is a high density image, high density pixel image. So if you look at over here, you don't see much features over here, but as you zoom in here, you can see more features coming in. So this says that there are underlying features over here. What matters is the length scale. Similarly, if you look over here in the river, there is a barge which carries the heap of sand, but a look from the farther side will not give you what's exactly the profile over here. Even closer look will give you the exact features over here. So the takeaway message is that the length scale actually take out whatever the features in the measurement. So how do you do the profile texture filtering? So when we do a measurement, we start with the total profile. So the total profile, it goes through a lambda S profile filter, which will give us a primary profile. So the lambda S profile filter will cut off all the fast moving signal. That means high frequency signal. So this will be typically noise, and then we will end up with the primary profile, which is called the parameters which are extracted from here is called P parameters, and then we will be removing the tip and shapes are removed. So now we have ended up with a profile something like this. As we mentioned in the first slides, we know that this texture contains a roughness as well as waviness. So the aim is to extract these two parameters, which can be done using cutoffs such as lambda C profile filter, which will give only this region, which encompasses only the roughness, which is the high frequency part in the profile. And the waviness can be extracted using the lambda F profile. So this bandwidth over here will take out the waviness profile from the filter, from the profile. Sorry. Now in the ISO and ASME Stylus profile filtering, so here we collect the real profile data from the sample surface, and the total profile is actually an unfiltered data produced by the Stylus profiler. A primary profile is, these are the definitions basically. You don't, I mean, it's interesting to know the theory behind it. So the primary profile is the data produced after applying short cutoff filter to the top file. And once you look at the primary profile, you can see there are a lot of variations, very fast changing variation, as well as very slow changing and intermediately changing variation. So as we discussed earlier, this encompasses multiple wavelengths. So you can, as you can see, there is a primary profile which we were started with, and then there is a very fast-moving one, which is a roughness profile, which is a high-frequency one, and then there is a waviness one, which is a relatively slowly moving over the primary profile, and then there is a slowly varying form from this. So how to extract this? So this is a detailed description of how to extract this one. So roughness profile. So you need to select a special cutoff frequency which is less than the cutoff wavelength. So this will give you roughness profile. Basically, this will be a description of what we have discussed earlier with the figure. Now, for extracting the waviness profile, the special frequency need to be greater than the cutoff wavelength, which will give you a waviness profile. The important thing over here is that the cutoff which you select need to be relevant to your process. So it may not be relevant to some other process, but it need to be relevant to your process. So, and then shape of the profile will be something which is running at a longer wavelength. Now, let's look at some more into the theoretical part of it. So the traversing length, once you get a profile, the total length which you travel is called a traversing length, and the evaluation length is the length over which you're going to do the profile evaluation, which typically is less than the evaluation length because we normally cut off the end part of it. And then in terms of the Stylus profiler, we will keep a particular number of sampling length. So each of these sampling length will be less than the evaluation length. So so this based on the segments of the profile showing distances between peaks and adjacent valleys. So here you can see there are multiple heights over here, and you can define different sampling lengths in the measurement. So this is based on the standard which you define. So the reason which I mentioned over here is that, so depending upon the standard which you mention or which you follow, you may end up with slight changes in the roughness numbers. So if you look at the ISO 4287 standard, and the roughness definition over here is calculated over the number of sampling length. But in the ASME, the N is the number of data points of roughness profile over an evaluation length. So do expect if you are shifting from one norm to another norm, there will be some small changes. So now let's look at how we can do in practice, how we can do the filtering. So we will be starting with the total profile raw unelevated data. So in the DECTAC, you can see the Vision 64. You can open and then you can load the data into the software. Then you will be ending up with something like this window. So we will not be directly working on this. First and foremost, we need to level the surface. So the data leveling option can be applied on the surface, which can be taken with the right-click mouse on in the panel over here. Now, once you do the leveling, you can do a linear or curvature or whichever leveling you require, depending upon the profile you're working on. And once the once the leveling is done, you can move on to the roughness measurement. So to do the roughness measurement, as we mentioned earlier, roughness is about norm. So first, this is the kind of window which you get when you start with the filtering. So as you can see, the first thing which you should notice over here is that there are two norms over here. You can switch between these two depending upon which norm you're following. So here it is ISO 4287 is selected. Then later, you can select a different filter type. Here it is selected a Gaussian regression filter. So there are other filters such as Gaussian filter, then R squared, C, then to RC, then spline, second order Gaussian, and robust Gaussian. So these days, the ISO typically recommends the robust Gaussian regression filter. The key thing over here is that whichever filter you use, you need to stick with that filter between the measurements. So you may be doing the robust Gaussian regression filter, and please don't compare that with a filter which, please don't compare that result with something which you got out of a different filter, because it will vary, because it may not vary largely, but there will be a noticeable variation because of the algorithm itself. Now, after selecting the filter type, you can select the band pass. This is to select, to differentiate the waviness and the roughness. So here the cutoff wavelength is defined as 0.08 micrometer, 0.08 mm, and then the cutoff 2 is 0.8 mm, and or you can select short and long cutoff. This is depending upon whether you selected band pass or over these choices. Now you can select the total or primary profile from this window, and then roughness profile. Over here, the total profile will give you the PA parameters, and then roughness profile will give you the average roughness parameters. You can select RA or RZ or parameters of importance to you. And then waviness profile can be extracted from the data. So once you select OK, calculate, then you will end up with this kind of a window where you can get the data out. So now let's look into the Stylus profiler and the certain kind of filtering and the setting which you need to use. So if you are starting with a periodic profile which is having a spacing distance something like in this range, and you have a Stylus numbers within that range, you can actually coordinate. So you can actually coordinate these numbers and select which kind of cutoff you can use. Let's say your periodic profile, that means something like this. So you can see this, there are repeating patterns. So the distance between this and this is, let's say it lands in 0.13 or 0.14. And you have Stylus radius of 2 micron, then you will be using a cutoff of lambda C 0.8 and lambda S 2.5. So the evaluation length required for that will be 4 mm. So similarly, you can make use of this table to understand which kind of cutoffs to be used. So now we need to mention something over here, that the importance of the Stylus radius. Let's say if this is the real profile of this, the real surface under investigation. So we have two cases where there is a sharp stylus and a little bit blunt stylus. If you look at the data which we got out of the sharp stylus is different from the blunt one. The reason being that the sharp one can actually trace the surface very well, but the blunt one will be tracing more like a over the top. That means if there are very deep trenches over here, the bottom of the bottom of the stylus may not be able to access the surface. Okay, there are questions coming in. Let me mute over here. Now, how the data void density filters the data. So let's say if this is the profile and you don't define that enough numbers over here, then there is a chance that you will be ending up a kind of filtration. As you see over here, this is going to be the data, but since you measured, you undersampled it, you will be ending up with a different profile. So you need to make sure that you have selected enough number of data points for the surface profile measurement. And sorry, yeah, this has been missed. So this is an extension of the earlier discussion, where you have if you have a 2 micron radius stylus with a 60 micron 60 degree angles, then it can actually trace the depth very well. But if you have a 12.5 micron radius stylus and a surface something like this, then you will be getting a more like a convoluted figure, something like this, which will never be a representation of the surface. So how different is the areal roughness? So in the areal roughness, you can use different filtering over here. This is the robust Gaussian filter, as I mentioned earlier. These days, ISO standards recommends more on the robust Gaussian filter rather than the Gaussian filter. Second. Yeah. So rather than the Gaussian filter, if you this is a representation of how a Gaussian filter, the order differ from like once you change from 0th order to 2nd order, how the analysis is going to affect your sample. Let's start with the raw 3D surface data, and then if you use a 0th order filter surface, then this is more like a waviness, and then you get a roughness data. If you take a cross section over here, you will end up with a profile something like that. And a look at it will give you an idea that you are ended up with an artifact at the edges, also over here. So the recommendation over here is that use higher order robust Gaussian filter, which is evident from the image over here. The filtered surface is looking much better over here because this doesn't have any edge effects. Choose your filters wisely. Now, moving on to the robust Gaussian filter between the non-robust and robust Gaussian filters. So let's start with the raw 3D surface data and then with a non-robust one. So this will give a waviness profile and a surface profile over here. If you look at a cross-section data over here, this is an artifact because this is not a true representation of the surface. This will the non-robust algorithm give unnecessary depth in the profile. So you need to use you can use the robust filter, which will give a much better profile data over here, which is a true representation of the surface. There are consequences. That means there are trade-offs in this case, since the robust roughness, or even in the case of a second-order robust Gaussian filter, the algorithm is more cumbersome than non-robust Gaussians and zeroth-order filtering. So typically, you will end up consuming a little more time. But thankfully, because of the better computation power in recent days, that may not be a big factor in this case. Yeah, so this gives a sneak peek of how the how switching between different filtering techniques will affect your timing and the effects of artifacts and the form removal. So let's say you have a traditional Gaussian filter, which may be faster, but if you have something kind of a bow or circular features, cylindrical features, then as we have seen, you will end up with edge effects. So then the recommended one will be the higher order robust second order filter, but then you will end up with little more time. Yeah. So now how to choose 2D and 3D. So the question is why one need to want to go to non-contact measurement depending upon the process which you are using for manufacturing, such as different type of coatings or machining, etc. So sometimes you will be doing some manufacturing process where the surface itself is very small, and then the dimension requires a non-contact. The dimension is very small, or the inspection require a non-contact inspection. Then you need a 3D profiler, because otherwise, if you try to put the norms for the stylus, then the size doesn't fit in. Also, since it is a non-contact, the stylus doesn't even comes into picture. So similarly, if you look at the patterns, these are directional patterns, which is small holes or the patterns coming due to the turning or drilling or milling. In this surface, you have a 3D regular surface, which is a effect of a hone cylinder. So you can see there are crisscross patterns over here, but this is a very random surface. So if you want to do a measurement over here, you can actually use a stylus which and do a measurement across the datum. Then this will be a representation of the surface. But if you translate that analogy, that kind of method over here, it may not be a true representation of the surface, because the moment you turn the surface over one measurement over here and one measurement orthogonal to that, then they don't represent the surface, because they will give you different data. So in that case, you need a 3D profiler. And now the third one here, it's pretty random. So here there is no other option than 3D measurement. So conclusions here. So we have gone through the surface texture analysis for quality control and failure analysis, and surface texture measurement techniques such as AFM, 2D stylus, 3D interferometry, and focus variation. Confocal, this kind of techniques are discussed. And then choice of techniques, height, lateral resolution, vertical resolution, range, and speed parameters, how all these parameters will end up in a decision making for your proper product. Then filtering, understanding the profile, choosing the cutoff, and then choosing the filters. And since and we have done the filtering demonstration here. Yeah. Hello.
Dr. Aisha, I think the audio got some problem. This is Vichy again, your moderator. So now, okay. So there's a series of webinar listed on our website. You can check the website for the time and date for the particular topic of your interest. We are now entering the Q&A sections. Should you have any question, you can just send in and I'll read it out for Dr. Aisha to answer them. So we have a few questions. Let me read out. The first question is related to the filtering, the cutoff. How to decide the cutoff if one is not really aware of the process of manufacturing the surfaces? That's the first question, Dr. Aisha.
Yeah, so typically one need to have an understanding about the process to better decide the cutoff. as we mentioned earlier in the Stylus profile slide here. Yeah. So this will give you an understanding of which kind of numbers which you have to use. But if you have a non-periodic profile, something like this, then if you have an understanding from other methods, then you can use the range for that to set your cutoffs for setting the cutoffs and the evaluation length, and deciding the stylus, the appropriate stylus for the measurement. So also there are tables which I have shared earlier, which will give you a rough idea. So something like this, which will give you a rough idea on which kind of numbers you will fall in terms of method which you use. So also there is another powerful method which we didn't cover today, is the Ph.D. analysis. The power spectral density analysis is kind of it's a Fourier transform analysis actually. So what it will give you is that it will give you the kind of length scales present in the surface. So that is also a deciding factor in the in selecting the cutoffs. Yeah.
Okay. Thank you. So let me read out the second questions. The second question is asking about leveling of the raw data. Will leveling multiple times increase the error?
Typically, you don't have to do the multiple times leveling. So you need to select the proper, proper points to do the leveling. So if you have a very randomly varying one, you can even enlarge your selection. That means each of them you can average the left and right selection. So you don't need to do a multiple times leveling of that.
Okay. The next questions. The next question is asking about the roughness parameters. I think he needs more clarifications of RA, RQ, and RMS. Can you just elaborate a little bit more about RA, RQ, and RMS?
So the RA is average roughness. So you will have so this also depends upon multiple parameters, which norms which you decide. I will send you the this is who Shamsu Akbar. So I will send you the detailed description of which how you determine the numbers over here. So the RA is actually the RMS roughness. So it's an average roughness. So you will be having a mean line over which and how what you will be looking for is how it varies from the mean line. So yeah.
Okay. Yeah. For this audience, should you need more information, you can just email us, and then we'll answer through email, or we can contact you to send you more information. The next questions is if we have a 2-micron stylus, can we measure the profile in nanometer level? We did not mention whether it's a Z level or XY level, but Dr. Aisha, can you answer these questions?
So yeah, so if it is an as Vichy mentioned rightly, so we need to know which is it XY or Z. So if it is Z, yes, we can do. But if it is XY, then it's going to be very tricky. Yeah, because the DECTEC have a resolution of around 1 angstrom, so you can actually measure the nanometer level in Z.
Okay. The next questions is, I think, from the same audience asking about leveling. So leveling after scanning some time give errors result. Please suggest some guideline for leveling. Yeah, I think this may be a big topics that Dr. Ashar, you can elaborate more here, but we can certainly contact this audience later.
Yes.
Ashar,
So, if you are selecting if you are not selecting proper area for the leveling, then it can result in some error, especially if you are in the leveling surface itself. There are large variations. Then you need to be very careful about which area which you are going to do the leveling. So, but this is going to be a detailed topic, so it may not be covered at the moment. Yeah.
Okay. I think there's no more questions from the audience. Thanks again for Dr. Ashar for your very informative presentations about the surface roughness. I'm now passing back to Suteng, the host, to conclude this webinar. Thank you, Dr. Ashar.
Thank you very much, Mr. Lau and Dr. Ashar. Ladies and gentlemen, that concludes our webinar for today. We hope you have found it informative and helpful. We also look forward to your support in our upcoming Bruker webinars, as shared by Dr. Ashar earlier on. If we can provide further assistance, please feel free to email us at bns.asia@bruker.com. Thank you very much and have a good day ahead.